Guys, I'm coming back for my part 2 of physical chemistry, Raolts Law problem solving as promised a while ago, right? I'm giving you the example from solving for this Raolts Law topic 4, volatile solute introduction for the Raolts Law. Volatile solute meaning components of a class A and B, and this is volatile solute. Okay, so if we speak about volatile solute, that could mean organic liquid, like this, for example. It could be pentane, propane, chloromethane, chloroform, like this. These are so volatile solute. Okay, because we are used to the non-volatile solute, right? But this time, volatile solutes, which are variation for the formula to be used, but still the same concepts and principles, apart from those non-volatile solute introduction of the Raolts Law, which is more simpler compared to this. Okay. So as you can notice, this also problem or liquids, okay, no involvement of the aqueous solution of a solute in a solvent. For example, sodium chloride aqueous solution with water, no like that case. Okay, this is only solvent to solvent ideal liquid mixture. Okay, of component A, component B, or component A and B are the solutes. Okay, so we have another example. But before that, I will show you our formulas to be used. Okay, this one. Okay, take a look for the formulas to be used. Start. And if you want to write it down or record it on your sheet of paper or notebook, then you can do also. Okay. Very clear, okay? So this is it. The vapor pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent. So this is an ideal liquid mixture solution. Okay, and our total pressure is equal to partial pressure A, partial pressure B, partial pressure C. A, B, and C are components, cast components mentioned in the problems. Okay, if there are two, okay, if there are three, then proceed for your calculation also. It will not matter. Okay, so in ideal gas solution, we are equating the total pressure as the vapor pressure of the solution. B solution is the vapor pressure of the solution. Okay, so therefore we conclude vapor pressure of the solution is equal to the partial pressure of component A plus partial pressure of component B plus partial pressure of component C. If we have only two components, A and B gas solutes, then then we have XA plus XB is equals to 1. Okay, like that. So another formula is here. The relation of the weight fraction is represented in a small letter x. Okay, like this. Represented as capital P, and above in there's a circle. Small is equal to the mole fraction of component A. Partial pressure of component B is equal to vapor pressure of component B. So mole fraction of component A is equal to the partial pressure of component A divided by the vapor pressure of the solution, in which it is the summation or the total of partial pressures of component A and B. Okay, our mole fraction B is equal to the partial pressure B over the vapor pressure of the solution. And our graph beside these formulas we have here, right? It's just a letter X, something like that. Okay? So if you try to plot the values of XA and XB with its variables of pressures, pressure pressures and vapor pressures, something like that, then we can obtain a kind of graphical representation like this, meaning to say there is a linear, okay, linear graphical representation. Okay, it's not a curve, it's linear. Okay, so that's it. And this is also the formula. Okay. And we have another formula also in terms of mole. Is a mole fraction in terms of pressure fractions, right? Or in terms of pressures, okay? And then we have also mole fraction in terms of the number of moles. Is one. Okay? So normally, the density also will be given in this particular problem. Then if it's not, then you can find in the handbook or any textbooks the table of those densities of solvent at particular temperature, especially if the problem is mentioning the reference temperature in degrees Celsius and degrees Fahrenheit, then automatically, even if the density of a certain solvent is not mentioned there, then you can find in the textbooks in the table for that densities of various liquids and gases, something like that. Okay? So a lot of problems only giving directly the densities will be no problem. But sometimes it doesn't mention like that also. Okay, that's what I'm telling you now. Okay, mole fraction of A is equal to the number of moles of A over number of moles A plus the mole of B. Moles of component B. So moles, total moles of solution is equal to Na plus B. Small letter n, okay, is the symbol or letter representation for the number of moles. All throughout this discussion in geometric relationship calculation for chemical calculations, small letter n is always the number of moles. Okay, X is always the mole fraction, something like that. So density is equal to mass over volume. Okay, like that. And then also, if you know, it's called molar mass. So molar mass, small letter M, okay, representation. But other textbooks represented that as capital M. But me, I'd rather times the number of moles. But in here, in Raolts Law, this is organic solvent. Okay, volatile, additional volatile solute. Here I will explain to you because this is liquid. Do not try to think, but that's a liquid, it's already a solvent. No, it will also become a solute. Okay? Like that. Additional or volatile solute. Okay, but because what we understand that solvent is always liquid. Yes, it's always, but sometimes we introduce gaseous mixtures also. Okay, so our solute is a gas, or it could be as a solvent or a liquid. It doesn't mean all the time solute is always solid substances. That's my point. Sometimes it could be gas, sometimes it could be organic liquid. Okay, our solute. That's why here in Raolts Law, our volatile solute, our solvent, something like that. Okay? It's very clear now. And here is the problem of the Raolts Law for volatile solute. Do not equate the solute as a solid substance as discussed in organic chemistry. Always like that in aqueous solution. Such words. In Raolts Law, it could either be a gas. This is the very lengthy problem, right? Okay, you can read this one. I will give you 15 minutes to record the given information and what are required in this particular problem. Okay, what we're trying to do is to list all the given variables there. For example, the volume, component A and B, the densities of component A and B, like this, the vapor pressures of component A and B, like that, and there's no issue of the temperature. The temperature is remaining constant in this Raolts law. Okay, like that. And take note also the molecular weight, of course, of each volatile solute. In here we have heptane and toluene. These are all organic liquids. Okay, so we consider this as our volatile solutes in Raolts law. Okay, like this. This is the problem. I have no whiteboard, so I cannot write clearly. Okay, this is only a A4 size of paper, so it's very difficult for you to write out. So I'll give you more time to record and write the problem carefully. With formulas for this Raolts law, you need to listen also to me and go over your computation on what are being required in this problem. It will be better in order for you to understand clearly rather than listening to me. It's just the same because it's purely only substitution. Okay? Shift solve for linear equation like this. Okay, so I will read now. Okay. This is a problem example of Raolts law for volatile solute. 30 milliliters and 16 atoms of hydrogen is mixed with 50 milliliters of toluene, which is a chemical formula of 7 atoms of carbon and 8 atoms of hydrogen. The densities of heptane and toluene are 0.689 grams per ml and 0.87 lang siya grams per ml. Okay, respectively. The vapor pressure of heptane and toluene at 20 degrees Celsius. Of course, we have the same vapor pressure because they are mixed together. Okay? Sorry, we have the same temperature because they have mixed together. Because temperature remains constant. See, we must review. Okay, in our Raolts law, temperature is remaining constant. Okay, so vapor pressure are 40 torr and 21 torr respectively. Okay, like that. So A, what is the mole fraction of each substance in the solution? Meaning the mole fraction of heptane and the mole fraction of toluene. What is the partial pressure of each substance above the solution? Meaning the partial pressure of heptane, the partial pressure of toluene. What is the vapor pressure of the solution? Meaning the vapor pressure of the solution, which is the formula of the mole fraction of the solvent component A times the partial pressure of the solvent component A. And then letter also B component like that. Using the same is the mole fraction of each substance in the vapor phase. Actually, we already computed the mole fraction of the solution. Still in the solution without considering first the evaporation process. During evaporation process, the vaporization stage, it's already in the vapor phase. Okay, there are mole fractions in the solution. Okay, originally during that mixing, during the mixture of this liquid mixture ideal gas solution, there are also mole fractions after the evaporation of the vapor phase. So this vapor pressures, okay, no longer the number of moles. Okay, and now we will solve this one by one. Okay, A, mole fraction of substance in the solution. My gosh. Hello guys. The first thing to do is to record stated given in the problem. So we have components A and B. Heptane. Okay, heptane 30 ml. Okay, and then The density is 1689. Density is 1689. Per pressure is 40 torr. Then for flowing, we have L. Grams per ml. And the vapor pressure is 21 torr. The word respectively meaning sequence. It is mentioned chronologically. Okay, that we mean by respectively. Okay, like that. So what is the mole fraction of each substance? So A, and it then should be represented as H. Okay, to make it short, right? So XH equals to XH over XH plus, okay, the number of moles of toluene, number of moles of heptane over the number of moles of heptane plus the number of moles of toluene. Okay, so number of moles of heptane over number of moles solution. Okay, so it's very dirty now, right? Like this. Okay, and then our mole fraction of toluene is equals to, sorry for that bigger apology, it's not the mole fraction, it's the number of moles. Okay, always in the mole fraction. Okay, number of moles, because mole, so mole fraction, so that you can be not mistaken for that. Okay, and toluene NT over NT plus NH, so solution. So these are our basic formulas to be used in calculating the mole fraction. I will show you. Okay, oh my gosh, like this. So this is now our mole fraction of each component solution. Okay, now how can we get the number of moles of heptane? Okay, since we know that there is the density, then we can get the mass, right? Then since we get already the mass, then we can have the molar mass in terms of its molecular weight. Okay, since it is molar mass, it involves number of moles letter N. So we can solve for the number of moles directly for that by substituting the number of mass of the heptane that we get from the equation density is equals to mass over volume. Okay, like that. The same as the mass in the or from the equation density is equals to mass over volume. Okay, and after that, our value for the mass will be used for the molar mass computation involving number of moles N, and solve for the value of N for toluene. So we can have now both the number of moles NT and NH together, and we can solve the mole fraction of each component. Okay, our main problem now is the molecular weight of each component. What you have to do is to get that through its molecular weight. Okay, molecular formula, sorry, through its molecular formula. C7H16 for, so heptane, did not put right. So C7H16 for heptane. Heptane may octa, penta, mega, something like that. Deca. Okay, don't forget that one also. Okay, so this is heptane. And our toluene is a slight different from the benzene. You know, benzene, the formula of benzene is 6 atoms of carbon and 6 atoms of hydrogen. Whereas this toluene only identification already. Okay, we should put that in our mind. The toluene is the same as benzene, but the additional 1 atom of carbon, 7 atoms of carbon, and 8 atoms of hydrogen. Now, through that, we can get the molecular weight. Okay, like this. We need first heptane. For heptane, oh my gosh, heptane molecular weight. Okay, heptane. Okay. You can use molecular weight of heptane in writing only, so 7H16 is equals to, okay, 7 atoms of carbon, so times 12. 12 is the AMU, atomic mass unit of carbon. And then 16. And we have AMU for hydrogen is 1.008. So 16 times 0.008. 1.008. Pila man ang siya. Since it in calculator for this. Okay. This involves decimal box. It is very difficult to multiply a certain numerical figure, a whole number, to the decimal points number with decimal points, sorry. So like this, 16 times 1.008 is equals to, we have 16.128. Again, review, 16 times 1.008 is equals to 16.128. But if in the problem it's already mentioned, so a little bit happy if it was mentioned already. But normally, to trick the students, they will not give, okay, something like that also. But if you really have mastery for this, you can never be cheated. It's always have the molecular weight, okay, whether it's given or whether it's not. Okay, like this. So you have to add now this ones. 100.128. So our molecular weight, just remember that in molecular weight, formula weight, atomic weight, it's always grams per mole is the unit. Okay? Grams per mole. Other textbooks only put MOL. That's okay. It's the same as mole MOLE. Okay? Can be used interchangeably. It's understandable. Okay. That is for heptane, for toluene. Okay. C7H8 is equals to 7 atoms times 12. It's equals to 84. And 1.008 times 8 is equals to 8.064. For example, guys, if you have already computed the molecular weight of each component, sometimes the question will also be like this: which is heavier, component A or component B? Just this question is only common sense. So your answer will be basing on the molecular weight. If it has a higher molecular weight, then that is heavier to another, something like that. Okay? So, for example, which is heavier? An H2S, a hydrogen sulfide, or an air? Okay. Like that, then compute for the molecular weight to identify which is heavier. If you forgot the theory and principle behind for that, then the heavier is the one that is a higher molecular weight. Okay? And then problem, what's air? Because you don't know also the composition of air, right? You don't know, right? But the composition of air is always oxygen and nitrogen, and let's prove that later. For example, which is heavier, an air or H2S? So based on the theory already established, it's always the H2S, because it will be down, okay, on the bottom of the vessel compared to the air. It's heavier than air. Okay, it will be down, so it's very dangerous for the people because it always be very poisonous, toxic, and a killer gas. Okay, like that. But you can smell that if it is already a rotten egg, there's a concentration of the H2S. Okay, inside the vessel. If there's no such that like that, then
think there's no H2S. Or the only way to prove that is to do the gas testing of atmospheric gases inside the vessels. That is the most scientific approach to do and to measure the gases inside the vessels, something like to prove. Okay, but we are only have the question which is heavier, an air and H2S. So now, what is an air? So again, it's basing on the theory. The molecular weight is 29 pound per pound mole, like this, based on the my stock knowledge. Okay. And then if it is 29 per pound mole, okay, what is the gram mole for this? And you have to convert. Okay, you have to convert. This is an English system involving pound, right? And then we know also in basic mathematics in conversion factor that 1 pound is equal to 454 grams. Then automatically you can get and determine in terms of gram mole of the molecular weight of the air. Now, are we sure that that is really the molecular weight of the air? How do we know that? Something like that. So we should remember that air composed of nitrogen and oxygen also. By percentage of volume, 21% of oxygen, 79% of nitrogen. Then how can we get in terms of pound and grams for that? And we have a basis of calculation, something like that. Remember that? So always assume 100 grams like this. There's a percentage, 21% of oxygen, percent of nitrogen, then we can have in terms of grams, which we have the basis of calculation as 100 grams, like that, okay? If you can remember that in our chemistry during the topic of normality, you know normality and molarity, something like that, okay? So, but we don't question that, we don't want to prove that as long as we have the 29 pounds per mole, something like that, okay? But it doesn't agree, we have to convert that later. Never mind, just believe on the theory that H2S is heavier than air. Okay? So what is the H2S? Okay, 2 times 1.008 and sulfur is 32. Ganun siya. Times 10.008 is equals to plus 32. See, there is 34 grams per gram mole. So this one pound 454 grams, okay, like this, and also 454 grams like this, okay. So 29, the same thing. So I'll just prove that also. It doesn't matter for the declaration whether it is a pound per pound mole or grams per gram mole. It's just the same in declaration. See, I converted that here. 29 pounds per pound mole. So 1 pound is equal to 454 grams. Like let's convert. And grams and pounds. So 1 pound is equal to 454 grams. So we cancel the grams. So it's just 29 grams per gram mole also the molecular weight of air. And we have the molecular weight of the H2S, which is 34 grams per gram mole. So it is heavier than air. Because air is only 29 grams per gram mole. Because the problem is general. It's not being mentioned the elements and compounds. Only air. What's air? There's a lot of components, a mixtures of everything. Except oxygen, nitrogen, okay, it's O2, nitrous oxide, because our atmosphere is not already clean anymore. Okay? What God had given to us before is already perfect. 21% oxygen and 79% nitrogen. But through to the different industries releasing gaseous wastes in the atmosphere, especially carbon dioxide, carbon monoxide, it be no longer 21% oxygen anymore. It will be lesser, let's say 20.8, 20.7, 20.6, because it really eating up some of the particles of those oxygen through the reaction of other gases, the waste gases, carbon dioxide, carbon monoxide, nitrous oxide. So there's no perfect 21% oxygen already in the atmosphere. That's the logic and the common sense why when we do the gas testing, the reading is always 20.8, 20.8, 20.9. It's not perfect 21%. That's the reason, because some of the particles will react to other gases surrounded in the atmosphere. cannot see, but that's the theory behind, of course, like that. Okay, so but since basic theory spoke, so the molecular weight is 29 per grams per gram mole. That is lesser than that H2, so it's 34 grams per gram mole. So going back here, which area heavier, heptane or toluene? Of course, the heptane, because heptane has 100.128 grams per mole, and the toluene is, wait, 84 plus 8.064. The toluene has only a molecular weight of 92.064 grams per mole. So this heptane will sink faster than the molecular weight in the solution because it has a higher molecular weight. Okay? Like this, it is heavier, of course. Common sense. Okay. We have now the molecular weight of heptane and we have the molecular weight of toluene. Okay, now we have the densities, the density of each component. Heptane, toluene. Okay, this one. So, oh my gosh, sorry. This one. Okay, try to analyze. Okay, in the problem, the molecular weight of these components are not mentioned. We are the one who will find it. Okay, something like that. Okay, why this molecular weight? Because we need to solve for the number of moles in terms of the molar mass. Okay. Now, how can we do the molar mass? Now, this is now our another problem. So molar mass, the basic theory, the molar mass is equals to the molecular weight times number of moles letter N. See? As I told you before over and over again, small letter M molar mass is equals to molecular weight and the number of moles small letter N. Now we will substitute that for heptane. So molar mass is equals to molecular weight of heptane, obtained at our 100.128 grams per mole. Now you will be in trouble here. Okay? Because you don't have the molar mass yet. Okay, but your goal is to get the number of moles which is already here, linear equation. So for the value of N, then N is equals to the molar mass divided by the molecular weight of 100.128 grams per mole. So we can solve the number of moles, small letter N, linear equation, divided by the molecular weight of the heptane, okay, is equals to the molar mass divided by the molecular weight equals the number of moles, something like that. Now our molar mass, how can we get it? We can get that through the density. Okay, the density of heptane. So we are very lucky that most of the data are given here, perfect. But sometimes we need to think and to get one by one back by using our initiative, because it was not like that, because we don't have anything on the data. Because there are also problem solving that you will be shocked only one data is there, really. But you can get other data through the, for example, temperature only. Through temperature, you can get the pressure, we can get the density. For example, heptane at 20 degrees Celsius is being also discussed there. What is the pressure at 20 degrees Celsius? What is the other molecular weight, like this? Everything is being presented there. So even though there's only one given, you can solve the other, and you'll be afraid already because the formula has so many things to work with. Okay, like that. Sometimes there are like that also, especially in the open book examination. It will become a headache for us most of the times. Okay, because who like to solve complicated problems? Of course, nobody wants, right? We should always want an easier situation, just like our lives. We need to have an easier lifestyle rather than a complicated lifestyle, right? Normally, common sense. So that's like a problem also. Nobody wants a difficult problem. Always easy and simple problem we like. Okay? Unless you are really a explorer or something like that, and you need to challenge yourself every time, and you need to prove something that you are good, you're intelligent, you're smart enough, then you can show to your classmates that you are really good, then you will be happy if the problems are very difficult. Okay, but how about the average students? You don't like it, and the majority of your students don't like it. So it's not good, right? So the only way to show the support is to teach them and guide them also the one who are not really good, okay, like that. And don't be too showy that you are very intelligent, you're very smart, and then you will be, of course, your relationship will be affected to that because you are very boastful, okay? Like that. You should adjust to the classroom environment. Classroom environment talaga, not work environment. Of course, because it's a school, okay, a university, an institution, okay. So that is a room environment, something like that, or classroom environment. So you should adjust something like that, okay. But for me, I will be happy if the problem is very easy. Of course, like, okay. And then molar mass, the density of heptane is equals to mass of heptane, which is the molar mass, is equals to the volume of heptane. Okay, like this. Solve for the molar mass because we need to find it. Okay, is equals to the density of heptane plus the volume of the heptane. So the density of it is being mentioned here in our given as 0.689. Okay, 0.689 grams per ml times the volume, which is 30 ml. Okay, like that, and cancels that out. What left is the grams. 0.689 times 30 is equals to 20.67. Okay, the molar mass of heptane. Okay, I will show you this one. Okay, since we don't know the molar, okay, my gosh, sorry. Since we don't know the molar mass, we can obtain that through the density equation. So density of heptane is equal to the mass of heptane over the volume of heptane. Since we have the volume of heptane, okay, and we have the density of heptane, by mathematical operation, basic mathematical operation, you need to solve for the number of moles of the molar mass of heptane. Sorry, the molar mass of heptane will be equal to 20.67. So now we can substitute now in the upper portion. Okay, there. Okay, so you have now completed the data. Then you can solve now for the number of moles for heptane. Okay, like that. So I will just move up. Okay, like this. 20.67 grams divided by 112 grams per ml. Sorry. So 20.67 divided by, oh my gosh, sorry, 20.67 divided by 100.12. So our N is equals to, the number of moles of heptane is equals to 0.264. Now let's try this one by using the XA plus XB para hindi na tayo mahihirapan, di ba? To solve it individually for the mole fraction of the toluene, which is the XB, because it takes time to go like this. Okay, let's prove lang siya. Okay, later. Okay, and then the toluene, the number of moles of toluene. So the same thing we will be able to apply. Okay, so molar mass like this. Is there really substitution, right? And now I understand why the instructors, okay, will not love to discuss it systematically, okay, because it will take time, and they will think for themselves it's very easy, and then the students can really understand. But actually, the instructor should be patient to really do it in the same manner. Do not do it in a shortcut method, okay? This is a great test for the instructor, because this is again and again the same formula. Okay, it will take time, and it will be boring, something like that. But never mind. It's for tuluin. We'll do it systematically. Okay, tuluin. Anyway, we can still get there. Okay, patience is a virtue, something like that. Okay, 8 times the number of moles, and then we have the molecular weight of tuluin. Okay, tuluin. So 90, ano ito? Maklaro? But I can go again, fairness, 84 plus 8.06 equals to 92.064. Okay, then on 92.064 grams per mole and molar mass, then number of moles equals to the molar mass divided by 92.0624. Okay, 92.064. Okay, like this. And our mass can be obtained by the density. So density, mass over volume. Okay, density of heptane is very mentioned a while ago. This one, this one, 0.879. But we will not carry the unit because it's just the same. There's no variation of the units reflected or declared in this problem, so no need to incorporate. Okay, and times volume, which is that. So times 50, and then our mass of molar mass of the toluene is equals to 0.879 times 50 is equals to 43.95. Okay, grams. Substitute that here. So 43.95 divided by 92.064. So our number of moles divided by 0.4774. Okay. Now the mole fraction is always less than 1. Okay. Less than 1. Okay, so the total will be equal to 1. Of course, that's less than 1. Ganun lang siya. And if you can obtain a mole fraction is higher than 1. Okay, it's 1. So in the same manner with heptane, we can solve for the molar mass of the two, and after getting the molar mass, you can substitute that in the molar mass equation, something like that, and then you can get the value of the number of moles. The number of moles for toluene, okay, 0.477. All we have now, 0.477. So we can solve for the mole fraction of heptane, okay, in our letter A. My goodness. You can substitute that here in this equation, because I already presented the formula of the mole fraction of each component. So we now substitute individually, okay, like that. So the number of moles of heptane is in my another paper. Oh my gosh, so difficult. Okay, heptane is 0.2064. Okay, look at the addition, 0.2064. Okay, substitute that here. So the number of moles of heptane, again, 0.2064. And then the number of moles of toluene, we got that already as, where is that? Here. This one. The number of moles of toluene is 0.477. See? 4.77 is the number of moles of toluene. So substitute that in the mole fraction formula also. Okay, here. So 0.477 plus 0.477. Okay. Now we can get the mole fraction of heptane. So 0.477 plus 0.2064 is equals to 0.6838. So 0.2067. Oh, it's 1. If we add the number of moles of heptane, and what would be our mole fraction of heptane? So 0.2067 divided by 0.6838. So our mole fraction is 0.3023. Wow. 0.3023. answer. This is mole fraction on the other side. I encircle that one. So sorry, this one. I'll mark where I encircle that one. 130.23 is the mole fraction of heptane. So mole fraction of toluene, we can subtract 1 minus 0.30. Let's try only because it's in the real, so x, okay? And then if not, we will solve again this equation of the mole fraction. Maybe there's a deviation, I don't know. We will just try for the first time because I did not do this, okay, a while ago. Okay, 1 minus 10 actually by using the principle. Okay, 10 plus L, our x toluene, which with 1 minus like 0.6977. Okay, we use this for the purpose that this is very easy to solve rather than that one's very complicated. Okay, then if this fails, and we go back to the original mole fraction formula, right? So XH plus XT is equals to 1. So the mole fraction of heptane plus the mole fraction of toluene is equals to 1. Therefore, we conclude that the mole 30.23, which is the mole fraction of the heptane, and we obtain what's this? 0.6977. And let's prove that also by using the formula here, the toluene. Try lang siya. Okay, 477, so 0.477 plus the mole numbers of heptane, so 0.20 moles, number of moles of toluene, 477 plus. Kaliputang din. Okay, mole fraction. This is the mole fraction of toluene. With the number of moles of heptane or the number of moles of solution. Okay? Like, actually, it's just the same with the mole solution of using the heptane mole fraction computation. It's just the same. Okay? I just illustrate that one by one. Okay? So what's that? So 0.477 divided by 0.6834. It's the same. See? The toluene mole fraction is equals to 0.6979. So therefore, this is a correct answer. See? Our mole fraction is 0.6977 by using the number of moles of toluene plus the number of moles of solution. Then if we try also to use the theory and principles behind Raolts Law that states mole fraction of A plus mole fraction of B is equals to 1, we can also obtain the mole fraction of toluene XT is equals to 0.697 and also. So therefore, we conclude we can use now the X. If there are only two components, use the A component plus B component mole fractions is equals to 1. Because that is very easy to do. You can only substitute the number of moles directly, and you can obtain the mole fraction of the other component. Sorry. Okay. But if you want to make sure, no problem. You can also go back to the mole fraction of the component B, but it will take time. Okay. Well, you can still use the XA plus XB is equals to 1. Why not? Okay. As long as you have the correct A of the component first. Okay. This is already proven to be something like this, correct? Okay. Or else this will not become a law of Raolts Law. Okay, something like that. Okay, so again, the mole fraction XA plus XB is equals to 1. You can use that also to compute for the other mole fraction for other component, or you can use individually the mole fraction formula. Okay, of each component in the ideal gas mixture, in ideal mixture of the solution, something like that. Okay, so now answer natin. We already answered letter A, right? Okay. What is the mole fraction of each substance in the solution? So, heptane 0.323 and toluene 0.697. I showed you a while ago, it has been solved already, right? The X of heptane, or of the mole fraction of heptane, 0.3023, and then the mole fraction of toluene is 0.6979. Okay, and then we go to the number 2. What is the pressure of each substance about the solution? So each man siya. So if there is a word each, meaning individual component, English, each substance individually, okay, it describes individually what is the pressure individually of the two components, heptane and toluene. Okay, now we use the formula like this, letter V, sorry. We go first to the, of course, no, we go to the heptane. Because we left heptane as our component A, okay? So part, okay, is equals to the mole fraction of heptane times the vapor pressure of heptane. This one, okay? Partial pressure of heptane is equal to the mole fraction of heptane times the vapor pressure of heptane. Now we have the mole fraction of heptane, which is 0.323. Oh my gosh! So, ba yan? Parang may ano, may wind speed. Oh my gosh. So, 0.323. And our problem is, what is our vapor pressure? So, okay, our vapor pressure is already discussed here. I put that here already from the very beginning. The vapor pressure of heptane is, what's this? 40. It's already given. Okay? No heat rate. Or else, if it is not given, you will refer to the table of vapor pressure at certain temperature. It's already mentioned. Okay? So vapor pressure is 40 torr, right? Torr. So our pressure is also in torr. Okay? When 30 to 3 times 40 is equals, oh my gosh, 12.092. Okay, 0.092 torr. Bakit torr? Ang dami namang units of pressure. Torr talaga. Malay mo, gusto talaga niya ng torr. Diba? So partial pressure according to the mole fraction of heptane is already computed, and the vapor pressure is given in the problem, which is 40. Automatically, we get the partial pressure of heptane. Okay? Partial pressure of toluene, same thing. Mole fraction of toluene, we get already a 0.6979. Okay? By computation. Okay? And then the vapor pressure of toluene, it's in the given here. Okay. It's given 21 torr. Okay? The vapor pressure. So we substitute again. 21 times 0.6977. We have the partial pressure of toluene equal to, oh my gosh, 0.6979 times 21 is also 14.66 torr. So partial pressure of toluene. Okay. See, we now answer the letter D. The partial pressure of toluene and heptane already computed. We answer letter D already. States what is the pressure of heptane is 12.092 torr, and partial pressure of toluene is 14.66. We answer letter B. Okay. Letter C. What is the vapor pressure of the solution? Since we have now already the partial pressures of each component, then we can just add the two. Okay? Because the partial pressure of toluene, substitute directly the 12.092 equals to 26.74 is the vapor pressure of the solution. Okay? The pressure of the solution is 26.74. Vapor pressure of the solution is 26.74 by adding the two partial pressures. Now, Why 26.74? Because it has been added, of course. And then you can say, why is the pressure is becoming less? Okay, it should be answered because you are adding a volatile liquid. Okay, by theory, the pressure will decrease. The partial pressure will decrease. Okay, like that from, right, we have the vapor pressure of 40 from heptane, and it goes down to 0.092. Okay, and the toluene also, we have 21 torque, and it goes down to 14.4, something like that. Okay, or 14.66. Okay, like that. Because the partial pressure are accounting the density like that and the other given, but the 40 torque is just only the reference point originally. Okay, so in the solution, okay, it becoming reduced the pressure because of adding of the volatile components, something like that. But it's solute, okay, and it's being mixed with each other, okay, like that. So our vapor pressure solution is 66.74. Okay, now letter D. Meron ba D? Here's the letter D. What is the mole fraction of each substance in the vapor phase? So reference for the pressure fractions, partial pressure and the vapor pressure of the solution. Okay, like that. Okay, so letter D. Mole fraction is different, because the mole fraction above the solution is not vaporized. That's why it doesn't have the same mole fraction after vaporization stage. It's just mixing originally, not yet vaporized. So of course the mole fraction is not the same with the mole fraction during vaporization state. That's why you will wonder why there are two mole fraction asked. There's already mole fraction asked in letter A, but in the solution. In the solution, it's liquids undergoing now the vaporization state, meaning it was vaporized. Some of the liquid heptane, heptane, mole fraction again, in the vapor phase na tayo, so over the vapor pressure of the solution. Okay. Now you guess if our not we didn't solve yet. 26.74 supposed to. Oh, see, I am wrong with my hypothesis. The mole fraction in heptane in the vapor state will become higher. It's now 0.72 from, okay, from 0.30 to 23. Why? I need to know why. Okay, and the mole fraction of toluene will be pressure of toluene. It's not enough to get the numerical value. Let's analyze why it become higher, because I think it's lower, but it's become higher. Okay, okay, and the pressure of toluene is 14.66. Or it's, don't worry. Okay, but L anymore. Okay. Okay. So the mole fraction of this one, last, the mole fraction of toluene is 0.5482. The mole fraction of heptane is 0.723. So in the vapor state, it becomes 0.70. This 0.7223. So it became higher. And the mole fraction in the solution for the toluene is originally is what's this? It's H. 0.6977. Okay, like this. And then it will become 0.542. Like this. Okay. Kalas. Finished. Okay. And then add the vapor phase and the solution. Let's add this one if it is okay. Okay, add this one. Okay. 0.6977 plus 2 and 0.548. Because it's take myself. The separate one, the vapor phase and then the solution like this. Okay. Okay. And then it becomes the mole fraction of heptane because heptane has a higher molecular weight than the chuluin. Chuluin is 15482. Everything will follow sala. Okay, everything will follow if you have higher molecular weight. Okay, yes. Okay, something like that. Okay, and then if your density is high, your mole fraction is lower, something like that. It's only 0.5482 in the vapor phase. In the solution, xt 0.677 lang siya. Okay, compared to 0.7724 sa heptane. Ganun. Okay. Finish. Okay. But in the actual problem solving, you don't have to analyze one by one. If you have get the answer right away, then you should choose. If that is a multiple choice question, then just choose the correct answer. No need to prove because it's already there. It's in the Raolts. No need to justify. Okay, it will just take time. Okay, like that. And there's a lot of questions. Let's say 100 questions. Finishing solving that by using the formulas you learned. Okay, so no need to prove. Okay, unless it is a discussion like this for the purpose of discussion. Okay, like this. Oh my God. So already all questions are being answered. Okay. Where's that? Where's the phone? This one. Okay, this one. This question has been answered already. A, B, C, and D. There's a lot of questions. A, B, C, and D. Okay. In the examination also, for example, in the classroom examination, this will be also like this. Okay. But in board examination, it's only seldom like this. There's a lot of questions. Okay. It will take time this kind of problem, right? So they will reduce it to two questions only in one problem like that. But for the classroom instruction purpose, for the instructor, should be like this. There's so many required in one problem, very lengthy. Okay, and then during the board examination, it will be adjusted there. Okay, and there will be a lot of trial, and you will be shocked, something like that. For example, you are using the correct formula, but then when you get the final answer, it's not there, something like that. Really, okay, and it became a headache. Okay, and there are also sometimes that the problem solving is not yet discussed during the education in your college. It's not discussed. Maybe it was discussed, but lightly, something like that. Or you are sleeping, you don't know. Okay, but you will never encounter that one also during the board examination, and you will have your own formula. Okay, you have to derive. Okay, me personally own formula. Okay, because I cannot get really the formula I memorized. Okay, I wonder why like this, and it consumes all my time. Last, that will be the last. Okay, the very lengthy problem. Because my style, if very easy, I will I will do that first, and then the difficult will be the last. Because it's same value, it's only 1 point, like, right? So why you solve first for the very difficult one? It's just the same. Okay, so go to the most simpler question, right? So it can add you more points, right? And it was time captured. Okay, and then I make like blah 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 so and so, and then unluckily it was not there also the answer. Really, remember that one? It was not there, but a little bit closer. For example, the choices is 0.675, and my answer is only 0.5 something. Okay, and then that is the very near to the choices, and I choose that one. Okay, like that. And I never sure also that it's correct, right? Because after the examination, you will never see, oh, what's this correct like that? This will be totally eliminated. You know, why like this? Because the PRC will not show your answer sheet if it is really the true and correct. They check it properly, right? We don't know. Okay, this is computerized, but we don't know really. Maybe correct and they put wrong, something like also, and they will put wrong. We don't know really because they don't give back our answer sheets after that. Okay, how can we prove something like that? Okay, so better if there's an examination like that. After the examination, all the answer sheets will be returned. Okay, and then
prove it is really the correct okay scores. We don't know, right? There's no perfect in the giving the checking also. Okay, like that. But that's their system. We question their system. Okay, that's Kalas, Finnish Kalas. Okay, thank you so much. So thank you so much. If you think this video is haven't subscribed me yet, okay, and click the notification bell for Summer Babush. God bless. Wow.